In this video, I want to talk about polar representation of complex numbers. Now, this is going to be key to understanding geometrically what complex functions are doing. This video is very important. Feel free to rewatch it if you didn't think you got all the details. And also, as an added bonus, if you understand this point of view, it gives us new insight to trig functions. So if you've hated trigonometry because it had lots of list of formulas, trig identities to memorize, you might be happy to know that if you understand this point of view, it gives us a new way of understanding those and maybe even deriving those trig identities on the fly with very little to remember. Let's see what this is about. Okay, so let's say we're looking at a complex number z equals x plus iy. Here, just to avoid the complication, let's say this complex number is not zero. So I'll talk about how to handle the case of zero later. But if you don't have a zero, so you're not on the origin, you can draw a line from that complex number to origin, and you'll get some kind of a right triangle like this. Okay, and of course the angle here is measured counterclockwise from positive real axis. So we already know the length of this hypotenuse on this right triangle. It's called the modulus. The angle on this, angle that this line segment makes with the positive real axis is called the argument. Now, computer scientists here might think, oh, is this the argument of functions that I'm learning? No, it has nothing to do with argument from computer science. It's just called argument. Argument is just the angle. So don't think about it too hard. Okay, and we're going to denote that the angle that this complex number z makes with the positive real axis, arg of z, lowercase a here. And it's important to note that this angle is not unique. So if any particular angle works, you could add or subtract any multiple of 2 pi. These are always measured in radians to get other argument that also works. So it's sometimes that comes in handy, and other times it's a nuisance because there's multiple cases to check. But that's what we're going to call the angle argument. And also remembering relationships in trig, cosine is the ratio between the adjacent side to the hypotenuse. So if you bring the hypotenuse to the other side, you get the real part could be written as the modulus times the cosine of the argument, and also similar relationship with sine. The imaginary part could be written as modulus times sine of the argument. Okay, this idea of multiple possible angles is annoying. So sometimes we want to fix a particular angle. So there's really no reason to pick one angle over the other, but let's just try to make it a smaller number as possible, right? Or close to zero as possible. We're just going to say the principal argument is the angle between negative pi to positive pi, including the positive pi. So that gives a window of 2 pi radians. Any angle could be described with some principal argument, and only one possible angle there. So when we want to talk about the principal argument, we're going to use the notation capital A arg of z, right? So if I use lowercase, then it could be possibly many different angles. If I want to fix one particular angle, I will use the capital A, and that's going to be the notation we're going to be using. Okay, now this is the most important part of this video, Euler's formula. Okay, it's a very beautiful formula. E to the I theta is equal to cosine of theta plus I sine theta. So if we know the exponential function e to the x, in the exponent, let's put purely imaginary number in there. So I times some real coefficient theta. Then it traces a unit circle. So the reason why I say unit circle is that, remember from trig, if we take the ordered pair cosine theta, sine theta, that's the point on the unit circle. That's radian theta from the positive x-axis. And that's the point on the unit circle. And if you write that in the complex number notation, that's exactly that, cosine of theta plus I sine theta. So if you imagine the function e to the I theta, it starts, when angle is 0, it starts at the point, the real number 1. And as the theta increase, it will trace the unit circle in counterclockwise direction. When e to the 2 pi I hits, you come back to the point 1. If you traveled 90 degrees or pi over 2 radians, you'll hit I. If you traveled pi radians, you'll hit -1. So I hope that makes sense. So this is the key to understanding geometry in complex analysis. This formula, Euler's formula, this circular motion. Okay, all right. Let's maybe not prove this, but see a reasonable argument to why something like this could be true. And I think the way to see it is with Taylor series. So the reason why this is not a watertight proof yet is because we haven't proved that these Taylor series or power series works in the setting of complex numbers. For now, let's take this for granted. But let's see what the Taylor series tells us about the situation. So recall that the Taylor series of cosine looks like this. 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial and so on. So each term is alternating signs. We're looking at all the even powers of theta, starting with theta to the 0 is 1. And each of those are divided by all the even numbers factorial. Okay, so with the series notation, that's what the cosine looks like. The Taylor series for sine is very similar. The only difference being you count up the odd powers instead of even powers. And you start with the power 1. And you also alternate signs. Okay, so that's what the Taylor series for sine looks like. Let's also recall Taylor series for e to the theta. Okay, so e to the theta is actually kind of similar to sine and cosine, except you don't alternate signs. It's the coefficient is always positive, and also you go through all the powers, not just evens or odds. So if you add sine and cosine, you can kind of see why it kind of looks similar to e to the theta, but not quite, right? Because there's alternating signs. Let's see what happens if you plug in I theta into this Taylor series. So instead of theta here, we're going to have I theta. And when you have the second exponent, you also have to raise the I to the second power. So we get I squared theta squared over 2 factorial. Remember, I squared is -1. So this guy is actually a real number because I squared is -1, that's real. And because it's negative, it's exactly this guy, the second term from the cosine series. If you look at the third power, so I cubed could be looked at as I times I squared, and I squared is -1. So I cubed is same thing as -I, and then theta cubed over 3 factorial and so on. So again, we'll have a -I in front of it. And when you raise I to the fourth power, you could look at it as I squared squared. So -1 squared is +1. So I to the 4 becomes 1. Okay, and then the process repeats. So if you look at the powers of I, it looks like I, -1, -I, 1, I, -1, -I, 1, and repeats after the cycle of 4. I hope that makes sense. All the even terms are gonna be flipping between 1 and -1. And all the odd terms are flipping between I and -I and so on. So you could reorganize this, right? All the even terms alternate signs because of the even powers, right? It's gonna be positive at first. It's going to be -1 on the second term, and then it'll be +1 on the fourth term, and so on. So those combine to make cosine theta. And all the odd ones, if you multiply, if you put in the extra I, then it's going to flip sign as well, and that will take care of all the odd terms, odd powers. So at least if you believe that you can rearrange this infinite series into 2 groups, the even ones and then odd ones, and then recognize those as, oh, this is the Taylor series for cosine, and this is the Taylor series for I times sine, then you could, this formula would be true, right? As long as the reordering is justified. This is where we have to kind of borrow some results from real analysis. So in real analysis, it turns out that you can't always reorder infinite series, but you can reorder it when the convergence is nice. So in this case, it's uniformly convergent, and in such case, you can kind of reorganize the series and the sum doesn't change. So then this argument could be proved in a watertight way, but we didn't see that extra piece, so we'll just take it for granted for now. Okay, all right. So how does this help us? Well, actually, in a lot of different ways. But let's focus on the polar representation of a complex number. Okay, so remember, let's zoom back here. Right over here, we wrote down that x is r cosine theta and y is r sine theta. So I'm just kind of rewriting that. Okay, if we had the modulus and argument of the complex number, you could rewrite that complex number in this way, in terms of the modulus and the argument. R cosine theta plus I r sine theta. Now, this thing is very much like Euler's formula, except there's an extra factor of r. So in fact, it's actually r times e to the I theta, because e to the I theta is cosine theta plus I sine theta. This is how we're going to represent complex numbers when it's convenient to write it in polar form. So just write the modulus is going to be the number sitting in front, and then you multiply that by e to the I times the argument. Okay, so just a couple examples. So all these examples has modulus 1, so r is just 1. It's not being written here. If the argument is pi over 2, that's 1 unit going in 90 degrees up direction. That's the complex number I. E to the pi I is -1, e to the 2 pi I is 1. If we go 45 degrees, then maybe you remember cosine of 45 degrees or pi over 4 is 1 over root 2, or same thing as root 2 over 2, and the same with sine. So that's how you can compute these if it's a nice angle. Okay. Some properties. E to the I theta traces a unit circle, so modulus is always 1. Okay. If you look at the complex conjugate, that's the same thing as e to the negative I theta. The reason being, if you flip the angle theta across the real axis, getting an angle clockwise instead of counterclockwise is the same thing as negating the argument. So conjugate manifests itself as a negative exponent. That's kind of nice to know. If you 1 over e to the I theta is going to be e to the negative I theta. How to think about this? If you multiply e to the I theta times e to the negative I theta, you're going to get 1, right? So you could think about it that way. In fact, actually, you could show that kind of exponent rule that's true for real numbers. So like if you take some base to 2 exponents that are being added together, you could split it into 2 factors of the same base, with each of the exponent appearing in each of the factors. You could show that actually it still works with a complex exponent using Euler's formula. So on the left-hand side, this is cosine of theta plus phi plus I sine theta plus phi. Okay. And then on the right-hand side, you'll be multiplying. Let's see, what would it be? Cosine theta plus I sine theta. That's the first factor. You're going to multiply this to, I'm going to run out of room, sorry, cosine of phi plus I sine of phi. And then you can multiply this out. And if you look at the real parts of both sides of the equation. So the real part is cosine of theta plus phi on the left-hand side. On the right-hand side, there's two terms after you FOIL this out. And if you use this, the angle summation identity from trig, you realize that they are the same thing. And for the imaginary part, you use the angle summation identity for sine. And you can prove that the exponent behaves the way we expect, even if the exponent is imaginary, at least in the case of this base E. So that's really nice. Actually, if you think about it, like Euler's formula is much easier to memorize than the sine and cosine additive identity that we have here. So in your trig class, I'm sure it was covered once. And I don't know if your trig teacher stressed how awesome this formula is. But if you haven't memorized it yet, actually this helps you memorize it, right? If you remember that this is true, you could split the exponent for using the Euler's formula. You could work out the real parts have to match. So this would have to be the identity for cosine, and this would be the identity for sine. You get two trig identities for remembering one formula in this setting. And this is not just one trick. Euler's formula helps us memorize lots of different trig identities. We'll get to that more and more as the class goes on. Okay, so more properties, but let's state this in terms of arguments. So the exact same argument that I made before, pun intended. If you're looking at complex conjugate, that's a reflection across the real axis, right? The vertical flip, right? That also means that the angle, instead of going counterclockwise, now it would go clockwise. So the argument would be the negative of the original complex number before the conjugate. You could say the same thing about 1 over z. And if you look at this formula, when you multiply numbers, the arguments add, the angles add. This is actually a really important insight because it works like exponents. Arguments behaves like exponents for E. If you multiply numbers together, the angles add. In fact, actually, the way we can prove this is the next line. If you have two complex numbers with some modulus R1 and R2 and some argument theta1, theta2, you could just multiply and just reorganize the modulus multiply with each other. So the modulus is like a real multiplication. They stretch in the way you expect. Or I guess if R1 or R2 is less than 1, I guess you could think about it as it's shrinking as well. You have, if you look at the Euler part of the angle part of the complex numbers, they combine and the exponents add, right? So the product has the argument that's the sum of the two arguments. So that's really nice, right? Remember, we already know complex multiplication, right? We could just multiply like algebra. You could FOIL it out and collect all the real parts and imaginary parts together. that's for computation. But if you want to understand what the multiplication is doing geometrically, this is how we should think about it, right? The modulus stretches the way you expect, like we do with real multiplication, and the angles add. Okay, all right. And once you know Euler's formula, de Moivre's formula is actually dead simple. But basically, if you, on the left-hand side, we're looking at e to the I theta raised to the nth power. And on the right-hand side, we're looking at e to the I of n theta. And you're using Euler's formula on that. That doesn't make sense. You're on the left-hand side, you're taking the exponent n later after you use Euler's formula. Right-hand side, n is part of the theta. It's the argument, and you're using Euler's formula once. Okay. It seems very obvious if you believe Euler's formula. But actually, this could be used to get all the double angle, triple angle formulas in trig as well. How do you do that? So I think I asked you to do this for triple angle formula in the homework. So maybe I'll do double angle formula. So on the left-hand side, we could square the usual Euler's formula. And I'll get cosine squared minus sine squared plus 2i cosine sine. And then on the right-hand side, I get cosine of 2 theta plus I sine of 2 theta. Okay, so I just square Euler's formula. So what? On the left and the right-hand side, the real parts have to match, and imaginary parts also has to match. So this part should be equal to cosine of 2 theta. And this part, well, without the I, just the imaginary part is 2 times cosine theta sine theta. That's the same thing as sine 2 theta. So we got 2 more trig identities just by squaring an expression. And this is usually called a double angle formula for cosine and sine. We got 2 formula at once. And then it takes more work, but if you multiply another factor of cosine of theta plus I sine theta, do FOIL it out again, you should be able to prove the triple angle formula. Or if you're bored enough, you could do, heptuple angle formula, right? Like you can work it out if you felt like it. So that's neat. I mean, this is not a formula that no one wants to memorize, right? But in the back of your head, if you know this, if you know Euler's formula, you could work it out if you felt like it. I think that's more important. To being a mathematician is not so much memorization, but knowing how things work. And if you're not lazy, then you can work it out. Okay. All right. I think I want to end the video here. So I will see you guys later.